I'm very happy to be here, and I wish to thank the organizers and Pavel, first of all. He disappeared here for his incredible patience. I see. That made me possible to eventually come here. Well, still the memory of the previous conference has not completely erased, so I think it would be a good wish for Boris and his wonderful group of collaborators to wish them just to make it a sort of tradition every decade. And, well, Boris has not changed for the 10 years, so we have a chance. And I wish you this wholeheartedly. Okay, so variation analysis. What is variation analysis? I admit that here some people do not know this, are not acquainted with this term, and I just want to say just a few words about that. Variation analysis is a branch of analysis that was developed during a few last decades that was basically centered on studying well, not very good objects like non-differentiable functions, set-valued mappings, complicated sets, and so on, that lack usual nice properties studied in classical analysis, like differentiability, smoothness, analyticity, and so on and so on and so on. It was basically the need for this variation analysis came first of all from optimization theory, and optimization theory still remains maybe one of the main areas of applications and of variation analysis. But I will speak, of course, about some very specific part of, although very, very central part of this variation analysis, which is connected with two concepts that I wish to introduce immediately. This is the definition of the first concept. Definition looks maybe a little bit frightening, but it is indeed very simple. And this is an explanation of this definition. Suppose we have a certain set-valued mapping, which we can interpret as which associate with every state of the system, the set of states that could be, well, reached through certain, well, action, I don't know. So if y belongs to fx, if y can be reached from x, then let us say that f is R controllable, where R is a certain positive number at this point xy. If for any sufficient small t, this blue property is satisfied. So we can reach, oh, sorry, thank you. We can reach any point of the RT neighborhoods of y from some point of t neighborhoods of x. So this proportionality with R, this really. This I understand. Yeah, thank you. Well, okay. And we say that f is uniformly R controllable near that point if it is R controllable at every point of a neighborhood close to xy, of course, x bar, y bar, I'm sorry, with the same range of t's for all xy. And this uniform R controllability is precisely this covering property defined above. So that is that. The other property is called metric regularity. Again, it is maybe a bit frightening looking at that, but the meaning is very simple, because f minus of y is the collection of points that can be reached from given x, the collection of x such that this y can be reached from these points. Or the same, the collection of solutions of this inclusion, because f is a set for every x. So, and this really says that the distance from x to the set of solutions of this equation is controlled by this quantity. Usually this quantity is easy to define, to compute, and this is very difficult to compute. So it gives you some leverage to cope with just estimates of this sort. Well, in mathematical programming, there is a famous Hoffman estimate for systems of linear inequalities of that sort, and this was a starting point for that. But basically, these two concepts really have a really deep roots in classical analysis, which is connected with results like implicit function theorem, Banach open mapping theorem, and well, Sartre theorem, and some others. Well, actually, I will not need much beyond this concept as far as variation analysis is concerned. And just to warm up, yeah, well, this I forgot about that. You can give quantitative characterizations for this concept. You can look for a largest R such that this uniform controllability property holds. And you can look for smallest k such that this inequality is valid for in a neighborhood of this point x bar y bar. And really a remarkable fact is that these two concepts are equivalent. These two properties are equivalent. And moreover, we have this type of relation between the quantities. The surjection modulus, surjection rate of surjection, is precisely reciprocal to modulus of regularity, which makes possible to pass from one property to another without problem and use whatever we wish. So, okay, so to warm up, I wish first of all show these two classical theorems, really classical, really central theorems, in first in linear function analysis and the second in nonlinear function analysis. Of course, a standard formulation of these theorems do not include here this equalities and here this equalities as well. Well, this basically said that the surjection modulus of the smooth of a smooth mapping is precisely the same as of its derivative. And derivative is a linear operator, so we can go here to compute these things. Okay, so and just having this in mind, I repeat it already for the third time, forgetting about what was in the middle. To warm up, I wish to show you maybe the very simple, very complete actually, the shortest proofs of Lagrange multiplier rule for just this standard infinite dimensional problem of optimizational problem with a quality constraint and smooth cost function and map. And that is that. If let's consider this map, the product of f small and f big. If we have minimum at this point x bar, if it is a solution of the problem, then this map cannot be regular. It cannot cover neighborhood. It's quite clear. So it remains to apply Lusterni-Grace theorem and Banach open mapping theorem, doesn't matter, to find some lambda and y star such that this inequality holds. It is just elementary argument. So this is a complete proof. This is a little bit longer, but also very elementary. If f is regular at x bar, then we can easily check if f small is a Lipschitz function. Then this function attains unconditional minimum at x bar. Okay, and this function is simple, so we can write necessary optimality condition with this function using well, elementary convex analysis very simply. And so, and we get this we get the existence of y star such that this holds. And if f is not regular, then again, Lusterni-Grace theorem give us existence of certain y star such that this holds. So again, we get Lagrange multiplier rule with very little effort. So, by the way, this formulation actually allows to give not just first order, but second order conditions and high order conditions as well. And that's what was done actually. And it still probably provides for the shortest way to approach this kind of things. Not only for such problems, but for problems of more general structure. So, and passing to more general problems, I wish to mention that the italicized parts of this statement first and the second, is not connected with smoothness, is not connected with any differentiability. It is valid for all kinds of mappings, right? So in principle, you can use, if you have some machinery to deal with non-regularity, non-covering property, then you will easily get from this machinery necessary optimality condition in the problems. And that is more or less what I would like to talk about. And, well, more specifically, I wish to show how this type of ideas works to prove, well, maximum principle for optimal control problems with differential inclusions. I will formulate it a little bit later. But what I want to tell is, let me return back for a second here. So if you, I said that if you have some machinery to verify non-regularity, like, well, the Stirling-Grace theorem, to verify absence metric regularity or covering property and so on, then you can use it and get necessary optimality condition. But actually, it is not even needed. We really, in fact, we don't need anything to use that kind of ideas for proving necessary optimality condition. And this is the fact that is called here optimality alternative that I wish to state maybe in more details, because it is central. So let us consider this time a fairly abstract problem. We minimize f on certain sets, which can be very complicated, defined in a very complicated way, and so on and so on. And then it turns out that whenever you have a function phi, of which we require only that it is non-negative and lower semi-continuous, and equal to 0 at x bar. That's it. And in this case, if x bar is a local solution of the problem, then the following alternative always holds. Either there is a lambda such that this function has an unconditional local minimum, or there is a sequence xn converging to x bar such that the values of this function xn is very small compared to the distance from xn to q. And xn do not belong to q. They are not feasible points in the problem. Okay, and the function, this function, attains unconstrained, unconditional local minimum at every xn for each n. So in either case, we have or just one problem of unconditional minimization, or we have a sequence of the problems, and we a priori know already that the solutions in the sequence will converge to our solution, so we should not care about that. That is that.
Alex, sorry, but how is phi related to the set Q?
This is a right question. Of course, when we deal with practical situation, we choose phi well connected with the data of the problem. Of course, the important point is that, I'm sorry. The nice point is that in principle, you can get this minimization problem much simpler, much more convenient to deal with than the original problem. The original problem can be very complicated, and if you manage to find a nice phi to deal with, then that's okay. But formally, you do not require anything of phi except that. The proof is very simple. It uses Eklund's variational principle, actually. So I wish to show how it works for this optimal control problem. So this is the problem. This is in optimal control theory, it is now a pretty popular formulation. It does not include explicit control parameter. It includes just the collection of all possible velocities at every point, at every t, and that's it. And it is more general problem than the classical for Pontryagin formulations, for example, because we can include here, well, the feedback relations and and a number of other stuff. Okay? Okay, I will omit these technical things except for mention of the Lipschitz property, which will play a very essential role in the discussions. Although it's a technical thing, but nonetheless. So to explain what will be done further, I need some technical machinery of variation analysis. Very simple, that's all I need. So if you have a function Rn, which is finite at x, or if you have a set Q containing x, then we can define what is called Fréchet subdifferential, or Fréchet subdifferential is the set. Elements of the set are called Fréchet subgradients or something like that. If this inequality holds, if you look at that, it is more or less the same as definition of the derivative, but instead of equality, or right here, inequality. And that is that. But we are interested not that much in this Fréchet subdifferential as in its limiting counterpart. We take any point x, and consider all possible sequences, x and pn, converging to x in this way. It's called f-attentive way. Not just xn converge to x, but the value of the function converging, and pn converge to p, and we consider all possible p that we can obtain this way. And this is what is called limiting subdifferential. Well, if the function is smooth, is differentiable, then this limiting subdifferential reduces just to the derivative. If the function is convex, this limiting subdifferential reduces to the convex subdifferential. But otherwise, it could be a pretty ugly object. But, well. And this is, if we set a set Q and the point x excused, then we can view on the distance function to Q and define that kind of object, which is a cone, of course, as follows from definition. I forgot to write lambda here, I'm sorry. It is lambda times this subdifferential, this set. That is that. This relates to the proof, so I will not talk much about the technique of the proof, so let's go further. So this is the maximum principle in this problem. So far, I would not, for the moment, I will not state precise condition under which this maximum principle holds, but this maximum principle consists of 4 relations. The first relation, there exist some multipliers. Oh, sorry, lambda and p. Like in usual maximum principle, which is non-trivial, this pair, and which satisfied transversality conditions more or less the same as in every kind of optimal control problem. But the joint equation assumes this form, which in fact is extremely beautiful when you start to work with that, and it was a long way to get this relation. It is Euler-Lagrange inclusion. And the maximum principle is, as usual, you just know that this quantity takes maximum over all y belongings to this set, to the set of possible velocities. More or less the same. So the novelty here was, of course, here, but altogether it is a pretty different result, technically. Okay, now about the condition. So there was a long development, and basically the basic steps of the development. First of all, it was Smirnov in '91 who proved this result under the condition that f has bounded and convex value, and this type of relation is valid, which is basically that f as a function of x, set-valued function of x, is Hausdorff-Lipschitz. This is precisely that. Hausdorff-Lipschitz with Lipschitz constant k of t, which is summable. Then Lowen and Rockefeller dropped boundedness condition, and it was, well, very non-trivial step, because assuming that type of Lipschitzness for unbounded sets is a pretty strong requirement. But on the other hand, there is a definite need to work with unbounded sets very often. So they found some other relation, which basically shows that when you look at the bigger part of the space, you have just increased this Lipschitz constant in a linear way, in a certain sense. Then in 97, Winter and Chang, but for problem without endpoint constraints, and I dropped the convexity assumption, which was also a pretty difficult step, because proving okay. And finally, Clark recently improved this condition in a very natural and way, in a very beautiful way. So we must be sure that really for every n there is a certain constant such that this inequality holds at ball of radius n around the derivative of the solution. So that is that. So I wish to explain how this final Clark, this is, by the way, this is state of the art. This is so far the most advanced result in theory of maximum principle, and so on. So I just want to give a very brief account of the proof. And the first step of the proof, we consider f with bounded values but not convex. And we define the test function this way. So it is just a measure of violation of the constraints, nothing more. Okay? It's a very natural function. And if we apply this optimality alternative with this function, then we'll see that we have either unconstrained minimization of this function, or a sequence of points xn which solves unconditional, which provide for unconditional minimum of that kind of function. These are functionals very well known in calculus of variations. They are so-called Balsa problems. Probably the basic problem of the calculus of variations, the easiest problem of calculus of variations. The problem is that here we don't have differentiability. Not here, not here, not here. And so how to treat this problem was not very clear. And the necessary condition for Balsa problem was found in 96 by Rockefeller and myself, and it contained more or less the same, non-triviality here elementary, and the other three are more or less the same as in the in the maximum principle that I formulated. So applying the proof was pretty hard actually, and we used a lot of techniques, smoothness, duality, relaxation, and so on. But in the case we consider here, when f has bounded values, both these functions, both integrands are Lipschitz here. And in this case, the proof of Balsa theorem turns out to be much, much simpler. So you apply this theorem or to the single solution that we have in the regular case, or to the sequences of solutions that we have in singular case. There are some convergence analysis is needed, which I will, of course, skip. Fairly standard. And eventually we get the result for the problem with bounded values. So the next step would be, of course, to try to consider instead of f, as we know everything about case with bounded velocity, set of velocities, let's consider that kind of set, f at tx, intersected with that. No, I'm sorry, I started 5 minutes later.
No, not 5.
No, 4. Okay. Now I'm finishing. So the point is that it doesn't work. It doesn't work because the function phi that I wrote earlier, if we put fn instead of f there, may not be Lipschitz. And and it turns out that we have nonetheless a very nice way out of this difficulty. It is possible to prove not the real maximum principle, but a certain abridged maximum principle, which we state for y belonging only to that kind of sets, which in principle gives us everything eventually. It's quite clear. And for that purpose, to get it, the following lifting lemma works. I will not really read this lemma, I just explain its meaning. It turns out that we can lift our set-valued mapping by one dimensional up. And to get certain Lipschitz mapping, which projects to something even a little bit bigger than our mapping, but nonetheless, we need it only for the test function, not to the problem. And then we can apply more or less the same technique and go and get whatever necessary. So this is more or less the way. It is, it's really, the proof that you get this way is much shorter than the original Clark's proof, which occupies the issue of Memoirs of American Mathematical Society, which is something. It can easily be extended to problems with state constraints. Okay, so this is, okay, I will, more or less what I wanted to tell, but I have still 2 minutes. I have still 2 minutes. And I have something, I wish to say something which, well, for me, I think is no less important than, well, mathematics, of which I was talking about. And the something is the following. Well, I know Boris also for about 50 years. I think that after Professor Tikhomirov, I am the second one in terms of length of acquaintance with Bora. And he was actually my teacher in the university once. We had a lot of discussion of every type of stuff, including ethics and so on. We were very often, well, had different opinions. Boris was typically much more tolerant than me. But what I wanted to say is that in his actions and his behavior, Boris was always demonstrated the highest ethical standards. And I have a lot of examples of this sort. Of one of these examples I want to tell you, which, by the way, explains how Bora appeared in this institute. Well, most of you probably don't have really good idea what was the life in the Soviet Union in 70s and what kind of well, pressure normal people had to experience and so on. So people, okay, this is a story that can be spoken about infinitely. But anyway, so once a very well-known mathematician, logician, Yesenin Volpin, was arrested for his dissident activity, and he was placed to some psychiatric clinics. And those psychiatric clinics were even worse than prisons because lawyers were not allowed there, and well, attitude to people was very terrible. And then a number of people working in the university, 90-something, I don't remember, wrote a letter protesting this. And this letter was accepted by authorities with enormous indignation, I would say. So there was enormous pressure on the rector of the university, Professor Petrovsky, to convince people just to cancel their signatures. Probably there was some promise that the fate of Yesenin Volpin would be changed to the better. And so, well, I don't know. But anyway, Boris refused. Boris refused and actually was fired from the university after that. So, and there were some other examples which, well, I wish you would know, but there's no time. He doesn't give me time. Thank you.